Okay. So basically we have clarified the meaning of deterministic models. So one input, one output. The probabilistic models can be defined by adopting the opposite definition. Probabilistic models take uncertainty into account and therefore associate several outputs to the same input. Therefore, to the same forcing, several outputs may correspond. So, a probabilistic model is essentially non-deterministic, and it takes, as a consequence, uncertainty into account. And what kind of structure may have a probabilistic model? Because I gave to you an example of a deterministic model, and basically think that take into account this example, I forgot to tell you, is implicitly based in the application of a law of physics, which is the law of conservation of mass. This is basically, it assumes that the mass is conserved through the rainfall and off transformation. Indeed, the mass is not, strictly speaking, conserved because there is a coefficient which is usually lower than 1, because it takes evapotranspiration into account. But still, you can call it a principle of conservation of mass with some losses that you account for. So basically, how can I give an example of a probabilistic model? First of all, probabilistic models are a branch of statistical models. So let me explain what is statistics and what is probability. So statistics can be defined as a science will deal with the collection and analysis of data. Probability is the science that deals with random events. And there are links here. Let me see, there are links with this definition. There are links here, I don't want to look for them. So basically statistics is deals with the collection and analysis of data. And probability, let me say something more. If a science that makes inference about random events, makes inference. I just said in my previous definition was not complete. I said deals with random events, makes inference on random events. So basically, statistics is related to data collection and analysis and doesn't presupposes inference, which means that you may collect data and just show the data to people. Like when you observe a river flow and you compute the average and you say this is the average river flow for the Po River. There is no inference. And instead, probability is something more because first of all it refers to random events. Statistics not necessarily deals with random events. It deals with data. Probability deals with random events and makes inference, like you try to predict the outcome from a random event. Like for instance, if you get a coin and you toss the coin 10 times and then you just show the data, this is statistics. If you look at the data and say, oh, I got 5 crosses and 5 heads, so the probability of getting a cross is equal to the probability of getting a head and is 0.5. This is inference, because you try to analyze the outcome of a random event, and you try to predict the probability of the event. You try to make a prediction, like if I toss the coin for the 11th time, now you know, you may say, with the probability of 0.5, you will get a cross. So it's a kind of prediction. So basically, why we refer to random events? Why the probabilistic model refers to random events? Because we assume that our model that we use to estimate the river flow is affected by uncertainty. And uncertainty, the classical way to deal with uncertainty is through probability, to make inference. So basically, when you have a physical process that you fully know and you can fully define, you build your model by building a deterministic model, and because you don't have any uncertainty. So you know the process perfectly. Like if you want to drop something in the void, and you want to predict how long it takes to get to the ground, to fall along the vertical direction for a given distance, you perfectly know the physics of the process. You are in the void, so you can write a deterministic model to predict the time that is needed to reach the ground. And basically, you don't have uncertainty. If there is something which is uncertain in your model, and I will explain why in hydrology there is uncertainty. If there is something that is uncertain in your model, you need to model this uncertainty. And the way to model uncertainty is to use a probabilistic model which makes inference over the data in order to decipher uncertainty. Like tossing a coin, you basically, what you do is to perform the experiment and to estimate the likelihood of getting an head through repeated experiments. To provide you an example on a probabilistic model for estimating the peak flow, I need to ask you to be patient. I will provide you an example maybe today or maybe next week. But what is important that you understand is the difference between these two models and what makes the difference. What makes the difference is uncertainty. So for what reason in hydrology there is uncertainty? For several reasons. And one reason is then that when we observe hydrological processes, when we observe river flow, when we observe rainfall, our observations are affected by uncertainty. There is a measurement error, but there is more than a measurement error. It's not just because the measurement error is something that is always present, but in many measurements it's negligible. So for engineering purposes, you may consider that it's negligible. For instance, if you estimate the geometry of a river cross-section, of course there is uncertainty, but this uncertainty you can consider it negligible because it's the order of centimeters in like 200 meters. It's the uncertainty of the survey, it's negligible. But when you estimate rainfall over a catchment, think at this phenomenon, your experience, how much it is variable. It varies a lot. When you drive in a car and you get a storm, our experience suggests that after 100 meters the storm may cease, which means that there is a strong variability, spatial variability and temporal variability. You understand that to measure rainfall over a catchment, over an area, is extremely complicated, and it's impossible to estimate, to observe it with precision. The uncertainty is very relevant. So uncertainty in the observation is a reason for the presence of uncertainty in our models. Another reason is that it's impossible to define the geometry of the system. It's because in the case of the river flow, it's relatively easy. But think of the flows in the underground. How can you define the geometry of the system? Because it's impossible. And another reason is that, I mentioned to you, we don't know how these processes take place. We don't really know. We don't know if the water flows over the ground or in the underground. So all these factors contribute to create uncertainty. And this uncertainty will never be removed. This is my opinion. This is my interpretation. Some of my colleagues say that with new monitoring techniques and the progress of human knowledge, we will get finally, eventually, to defining hydrological processes with precise model, deterministic models. In my opinion, this will be impossible forever, because how can we get the capability to observe what is happening underground over a so extended area? Is not just a matter of a plot. It's a huge catchment. It's impossible. How can we define rainfall, measure rainfall with precision? It's impossible. So in my opinion, uncertainty in hydrological models will always be present. And therefore my conclusion is that the correct model should be a probabilistic model. Hydrological models should, all of them, be probabilistic. And again, this is my interpretation. And there is quite a considerable debate in the international literature about that. But I'm really fully convinced. I dedicated a lot of thoughts to this, and I'm really fully convinced that the most appropriate approach is the probabilistic one. And therefore, what we see is that we need to know something about probability theory. And therefore, my next step will be to provide to you the basic concepts, just the concepts that we need for designing these models of probability theory. In the classic approach, usually we start and somebody tells you, okay, this is the concept of hydrology, we need to know probability and statistics. And the students get bored because they don't realize why. I hope that in taking the opposite way, you can understand why I need to introduce you some basic concept of statistics. And, but there is another concept which is extremely important. The statistical or probabilistic model should be physically based. And this is extremely important. What we need is a physically based stochastic model. And why I say physically based? Because we are describing a physical process, basically. And I already mentioned to you, and it's written here, that strictly speaking is not just physics. Strictly speaking, there is ecology, there is chemistry, because the water flow is also affected by chemistry. Pollution makes water denser, and therefore, chemistry is also relevant. But of course, the main laws are the laws of physics. We are talking about fluid mechanics, basically, because it's movement of water. Fluid mechanics is physics. So the main concepts are physics, and therefore, to be short, sometimes we say physically based model. And one may be, to be more comprehensive, one may be process-based model. But I often use physically based because it delivers, I think, the concept. And this physical basis should be accounted for in the probabilistic approach. Because if there is some uncertainty, there is also some physical knowledge. And we don't have to forget it. We don't have to drop it. The physical knowledge reduces uncertainty. And therefore, for the only fact that we realize that there is uncertainty and will never be removed, we don't have to stop trying reducing uncertainty. Uncertainty must be reduced because now it's too large. I said we need solutions. And in saying that we need solution, I mean we need also reduced uncertainty. And therefore, we have this mission, this challenge also to accomplish. And reducing uncertainty means to use the physical basis, to try to describe the process by using physical laws as much as we can, and then what remains left out is uncertainty. And uncertainty should be should be modeled through a probabilistic model. And therefore I say physically based, probabilistic model, or stochastic. Probabilistic and stochastic, please, let's assume that they are synonyms. Because my will would be to avoid to use the term stochastic and to use probabilistic. But I am used to it, and therefore when I say stochastic, please assume that it's a synonym of probabilistic. They are not really synonyms, but let's assume that they are. Okay, basically stochastic means probabilistic. And therefore, what we need is a model that is able to use the physical basis as much as we can, plus probability to estimate uncertainty within a unique model, a unique one. So my conclusion is that we don't need any classification. The model that we need to use to estimate the peak river flow is a physically based stochastic model. And then, of course, the structure can be different. But the framework must be unique. And why is that? Because the mechanism, the physical mechanism is just one. So we need one class of model to model it. And before I move forward, let me make clear one thing. When I speak about uncertainty, it's the model that is uncertain, not the physical mechanism. The physical mechanism is the physical mechanism. It has only one trajectory. And once that we observed it, it's not uncertain. It's there. It's when we speak about predicting, implicitly, we imply a model. And then uncertainty comes into play. Okay, so when we speak, we can't say the rainfall runoff transformation is uncertain. Absolutely not. It's the rainfall runoff model that is uncertain. And sorry, this may seem something like philosophy, but it's not. It has an engineering implication. Okay, because it's extremely important. Because we cannot really say that the mechanism is uncertain. The mechanism follows the laws of physics, the law of ecology, chemistry, and it has its own trajectory. It's not uncertain. It's the model that is uncertain. It's like the elections. The election, the process of making an election, is not affected by uncertainty. People vote, cast their vote, put the vote in the ballot, and then some people take the envelopes out and make a computation. There is no uncertainty in this process, absolutely. And then you show the results. It's certain. It's like rainfall runoff. There is some rain, and the rain flows. We don't know where, but it flows downstream, and then gets to the river, and originates a flood. And it's not uncertain. But when we try to predict the outcome of the elections, then we use a model, and the model may be based on pools, on analysis of limited samples, and there is uncertainty. And therefore, they give an estimate usually. They tell you maybe the party gets 40% plus minus 5%. It's a model that is uncertain. It's extremely important in order to get the concept, to get it. Okay, so now I should move forward with an example. Let me see if I forgot something. Everything that I mentioned is written here. Okay, so basically, and please, if you see mistakes here or even spelling errors, let me know, because this is growing up. I wrote this page yesterday, so I read it and I used also the grammatical corrector, but still something. Or if you think that something is difficult to understand, in my will, this should be perfectly understandable. If you see something that can be improved, just let me know. Let's discuss. Okay, so unfortunately, if you want, we now need to introduce some basic concept of probability theory, and I will be very short, but I'm not sure I close today, but I will be very short and very applied, very engineeristic, let me say, and. But we need to know what is probability. How can we define it? And basically, probability describes the likelihood of an event through a measure, through a real number. And this real number is comprised between 0 and 1. So if an event is certain, we say that it has a probability of 1. If an event is impossible, we say it has a probability of 0. So it is extremely simple. And of course, how can we define this measure? Because, okay, probability can be defined as the likelihood of an event to occur, but how can we define this likelihood? And this is the subject of, has been and still is the subject of a very interesting debate. So basically, if you say, what is the probability that tomorrow rains? So you may look out of the window, they say high probability. So And also you may look at the forecast of the weather, so you may say high probability something like 0.8. But how can you really say 0.8? What is the practical way of defining the probability? So there has been several definitions of probability that have been proposed by the literature. The most popular one is the definition that refers to the Kolmogorov axioms. So basically, in this way, we define probability by imposing conditions on this estimate. And the conditions are driven by the Kolmogorov axioms. They are very simple indeed. Very, the first axiom says that probability is greater than 0, greater or equal than 0. So it's a positive measure. Okay, fine. I already said, I anticipated that because I said it's comprised between 0 and 1. Okay, the second axiom says that the probability of the certain event is 1. Fine. So basically, I can simplify the two axioms by saying between 0 and 1. Probability is between 0 and 1, including the extremes. Okay, and then there is a kind of additive properties. If you have disjoint events, the probability of getting one event and a second event, so the union of the two probabilities, is given by the sum of the individual probabilities, provided they are disjoint. So this is what the third axiom says. And that's it. These are the conditions. And then there are some implications that are written here. So basically, the definition, you say, it's very flexible. Your number should be guessed, probability should be estimated in a way that it is comprised between 0 and 1, and the additive property holds. Okay, but this is not enough if we want to get a number. So basically, how to estimate this number? Let's first of all refer to let's first of all introduce a new concept. I'm speaking about events, but we need numbers. And so for the peak flow, indeed the flood is an event, but we measure this event with a real number, which is the peak flow, or the hydrograph. So basically, in order to deal analytically with events, we need to convert the event in a number. And this association creates what is called this association between a random event, random. Probability, I remind you, deals with random events. So to create this association between a random event, the flood, and a number, which can be integer, real, creating this association means introducing the concept of random variable. The random variable is an association from a random event and a number. Okay. Then this number can be discrete or real. Let's assume that it's discrete, okay? So basically it is discrete when you, for instance, say, associate the event to the occurrence of an exceedance, like the event is the overtopping of the Levy. So basically you may say that when you have overtopping is 1, the random variable takes value 1, and when you don't have overtopping, the random variable assumes value 0. This is a binary random variable which is associated to the event of overtopping of a Levy. This is a case of discrete binary, in this case random variable. If you associate the flood to the peak river flow, it's a real random variable. And let's refer for now to a discrete random variable. There are different methods proposed for estimating the probability of an event. The most used one is the frequentist definition, Basically, you estimate probability, you assimilate probability to the frequency of occurrence. It's very easy. So let me make the example of the overtopping of the river. Your event may be the annual maximum flood, which you quantify with 0 and 1 if you had no overtop and an overtop respectively. You take 10 years of observations, you have 10 numbers. Let's suppose that you had 1 overtopping. So basically what is the probability of getting overtopped is 1 over 10, 0.1. And it can be easily proved that by assimilating the probability to the frequency of occurrence, you meet Kolmogorov's actions. The frequency is comprised between 0 and 1, and if you have disjoint event, the sum of the two probabilities gets to 1. So in this case, if I had 1 overtop in 10 years, the probability to overtop is 0.1, and the probability of not overtopping would be 0.9. So the additive property holds. And you can prove it with, also by tossing a coin. Tossing a coin, you have 2 events, 2 possible occurrences, head and cross, and of course if you make experiment, let's suppose that you toss the coin 100 times, you would get close to 50 times head, and this means that the probability of getting an head is 0.5. The probability of getting a cross is 0.5, and therefore the additive property holds, because if you sum the two probabilities, you get to 1. And by the way, a famous statistician of the 19th century, Pearson, tossed the coin 24,000 times and got about 12,024 times the head. And he did that because he wanted to prove that probability theory, the frequency of occurrence converges to the probability of getting an event. Because you know, when you assimilate the frequency of occurrence to the probability, of course you need many experiments. Because if you toss the coin just once, you can't get the probability of getting, you need many experiments. So you wanted, this definition applies if the number of experiments, the number of trials, they say tends to infinity. And this is a good way of estimating the probability, frequency of occurrence. So keep in mind, this is the first concept that I want to give you. How can we estimate probability? Frequency of occurrence. This is the first solution. But of course, in order to apply this solution, you need the possibility to perform repeated experiments. Okay, so what is an alternative? An alternative is the Bayesian definition, and it means that you assign probabilities by perception, by feeling, by guess. This is possible. If you cannot perform an experiment, like for instance, you get a coin and you cannot toss the coin. So basically, if one asks you, what is the probability of getting that? You look at the coin and say, yeah, it looks fair. So my guess is that the probability of getting an head is 0.5. This is by guess. This is a Bayesian definition. And then you may decide to perform some trials anyway, and then you can update this guess. So if you have some information, you are allowed to update this guess. But when you estimate the probability by perception, feeling, guess, this is a Bayesian estimation. Of course, you have to make sure that Kolmogorov axioms are met. So if you say the probability of getting the head is 0.6 and the probability of getting the cross is 0.8, I would say no, this is a bad estimate. Okay, the sum must be 1. Or if you say the probability of getting an head is -1, absolutely not acceptable. But Bayesian probability is extremely important because, for instance, when you make predictions for the outcome of the election, you cannot perform 100 elections and make a prediction. You make a prediction basing on your perception, your guess. So when we say it's likely that that party wins the elections, it's your perception. this is a Bayesian estimate. And also, when you go over a watershed, and somebody asks you in real time, what is your estimate for the peak river flow? You may find a guess. Your guess is based on Bayesian estimation of probability. Implicitly, when you make a guess, you are associating this event to something uncertain, and when you provide a number, this is a Bayesian estimation of probability. Okay? So basically, you already understand that even if we want to use a probabilistic model to estimate the river flow, we may have several different options. But let's now converge to an example. And let me go back, because there is something more that we have. Yeah. So basically, given that we refer to numbers, it is very useful if we had, for instance, for the peak river flow, an analytical function giving the probability of a given value of river flow. So something that can be written as in this way: probability of Q is equal to some function of Q. And this is the probability distribution. Keep in mind that so far we defined probability only for discrete events. Because, you know, in order to be able to count the outcomes, you need to define the event. And the event can be, for instance, overtopping. It's very clear how you can count the number of overtoppings. It's very clear. But let's suppose that your event is the occurrence of a given river flow, which is a real number. How to count the number of outcomes? The real number has an infinite number of digits. So when you observe a value, how can you count the number of times that you get 10, 1.1, 2, 3, 4, 5? You observe the river flow, you will never get this value, never. You may get a similar value, but the next digit could be, or the last digit could be 6 and not 5. It's impossible to get this value. So a question arises, how can I count this? So the only way, because you are dealing with a real axe, so this is Q, and basically when you get your observation you fall here, the only way of counting these outcomes is to divide the real axis in intervals, so to make the real variable discrete. And this is what I did when I considered the overtopping. I divided the real axis in two intervals. The lower one, overtopping, and the upper one, overtopping. So this is the only way. So for continuous random variable, you need to divide them in intervals in order to count the outcomes. Okay, so what is the probability distribution then? It is an analytical function of this form, which is very useful because, you know, we need to know in practice the probability for several flow values. Why is that? Because, as I told you, the peak river flow must be estimated for a return period, and the return period is an estimate of the frequency of occurrence. So you already understand that the return period can be related to probability. Because I said probability is assimilated, can be assimilated to the frequency of occurrence. The return period, in turn, is related to the frequency of occurrence. So basically, the probability distribution is useful because by knowing the return period, I can estimate the probability, and then by applying this analytical relationship, I get the peak river flow. So this is extremely useful. So basically, our problem, which is estimate the peak river flow for a given return period, can be fully resolved by estimating the probability distribution of the peak river flow. This is very related to engineering. I mean, what I need is to give this value to the person, to the structural engineer that designs the bridge. Maybe the river flow, maybe a river stage, it doesn't matter. And I can perform my task by estimating the probability distribution of the river flow. If I do that, I can also provide an estimate of uncertainty, which is needed to the decision maker. The decision maker needs to know the design variable and also its uncertainty. Otherwise, he cannot decide. I propose to stop here for today, and what I just would like to say, studying civil engineering and studying hydrology sometimes implies that you have to study some boring theory. And the theory can be boring because it's difficult to understand, or can be boring because it's indeed something that it's not interesting to you. By taking this approach, I hope I clarified that I'm just introducing the concepts that I need, and I hope I was able to clarify the implication in practical design. And, but still, I realize that this concept may be something that it's, of which you don't see the immediate utility. I ask you,